Okay, I think that's recording. Okay, welcome to class. So first things first, I have copies of the syllabus and problem sets up here for those of you who may not have gotten one last time. A couple course announcements, the easy ones first. As you have noticed, we have a much more convenient room than we did last time. One comment is that the lunchroom is on the other side of this thing, so hopefully this will provide sufficient insulation. The next announcement, my office hours will be Tuesday instead of Thursday, or Thursday instead of Tuesday, one of those. Thursday instead of Tuesday. I think I said that in the email. From 2 to 3, although based on the status of the next announcement, that might change. The TA's office hours were scheduled last time, Friday from 2 to 3. I've reserved the piano room, which is on second floor for that purpose. I actually do not think they will hold their office hours there today because we have not done anything yet worth bugging your TA about, hopefully. And also, you don't have a problem set due next week. So the first problem set will be due a week from Monday. Now for the non-trivial announcement. I shouldn't use the word non-trivial. It's kind of insulting. Now for the even more less trivial announcement. So there's been some discussion as to whether or not we should move the class forward by 30 minutes. It was currently scheduled officially it was scheduled to be from 12:30 to 2 because 2 to 5 is the officially scheduled time for the modern physics lab. But I'm now informed that that is only virtual rather than actual, and that instead thank you. Instead, that lab is whenever you feel like showing up for the lab. So there's no reason not to push it forward by 30 minutes. However, I know that there's at least one person in the class who is going to a class from 1 to 2:30. And so this would mean that this person has to miss 90 instead of 60 minutes of this class. Is there anyone else who would prefer not to move the class forward by 30 minutes? Who's the person who's been emailing me? That person might not even be here. Okay. There was one person who's taking, it's not the fluid mechanics class, which is what I said in the email, it's the condensed matter physics class, 660. So who is it who's taking 660? Not even here right now. Okay. So yeah, there's one person who's taking 660, which is from 1 to 2:30. But there were some other people who are not here right now, who are in a class until 1 p.m., I guess. This is the anthropic principle applied to the scheduling of physics classes. Most of you don't know what the anthropic principle is, which is good. You don't want to know. So let's take a little vote just so that I can get an idea. Who would prefer to have the class move forward by 30 minutes? 1, 2, okay. And why would you prefer to have it move forward? Just because because it's more fun, or what? Are there other conflicts that you have?
I have a meeting.
You have a meeting right now. Okay. Are there other? What are the other? Yes.
Well, for me, I can't leave here until 3:50, no matter what happens.
I see.
So it doesn't matter.
Yeah, that's not a valid reason. No, I mean we're talking about people who might have to miss class. My goal is to have as few people miss other classes as possible. I mean, that's, I think, the most important consideration. Is there anyone who would, and you're missing a meeting, so that counts as a class. Is there anyone who has to miss something? Okay, let's be a little more systematic. So option 1 is 12:30 to 2. Option 2 is 1 to 2:30. So how many people would be able to not miss something that they are currently missing if we had option 2? So that's you. Anyone else? You're just scratching your head. You're not saying. Okay. So what are you currently missing? Oh, you sent me an email. Yeah. Okay. So there are 2 people who are currently missing 30 minutes of some class in order to be here right now. Are there any people? I know that there's at least one person who I think is not here who has to miss. So is there anyone who has to miss a class, who would have to miss a class if it were scheduled from 1 to 2:30, and so would then prefer to have it scheduled from 12:30 to 2, as currently posted? Okay, so it looks like there are 2 people who would be saved by having it moved from 1 to 2:30, as opposed to 1 who would not. Maybe what I'll do is I'll take this poll again at the very end of class, because there might be some people who are currently missing something. So I want to make sure our data is reliable. But if that is indeed the case, then I will go ahead and try and reschedule the class by 30 minutes. I should say that I am recording the lectures. I think that it's better to go to real lectures than watch the recordings. First of all, I can't promise I'll record every single lecture just because of technology. And second, I'm much more fun than a computer screen, and I think it's much easier to pay attention and to absorb material in real time than it is virtually. So I think that watching the lectures online is something that is possible, but I don't encourage it on a regular basis. Okay. Any other? So we'll do is we'll take a poll at the end of class again, and if the numbers don't change, then I will go ahead and see if I can reschedule from 1 to 2:30. The other advantage of 1 to 2:30 is that I think I could get us a better room than this one, but that's a relatively minor concern. Any other questions or comments of an administrative nature? Okay. Well, then let's go ahead and get to some physics. Last time we began our discussion of Lagrangian mechanics. So let me just zoom in a little bit here. Is that big enough? I think that's probably big enough. So last time we began our discussion of Lagrangian mechanics. So let me just remind you of a few of the basic features. So we'd considered a system with some number of parts m whose positions are denoted r alpha, where each r alpha is a vector denoting the three-dimensional position of a component of the system. And alpha here is an index which labels the different components and runs between 1 and m. And in general, these various components of the system obeyed some constraints, which means that the number of degrees of freedom of the system, which we would call n, would be less than or equal to m. And the number of degrees of freedom would be equal to m only if we have a system of free particles which do not, or free objects which do not obey any constraints. And our goal was to come up with a formulation of mechanics such that we can describe everything in terms of some dynamical variables. So what we would like to do is choose some dynamical variables. 3m. I'm sorry. Thank you. Because the number of degrees of freedom is less than 3m, not m, because we're in 3 dimensions. And so the dynamical variables will be qi, where I runs from 1 up to n, the number of degrees of freedom in the system. And these dynamical variables could be coordinates of the parts of the system in some convenient coordinate system, or they could be any other more complicated parameters that describe the state of the system. And the only thing that we demand is that the QIs uniquely specify the state of the system so that, for example, we can write the R alphas as a function of the QIs, as well possibly as a function of time, if, for example, the QIs describe the positions of the parts of the system in a rotating or accelerating coordinate system or something like that. So our goal is to then reformulate the Newtonian laws of physics in such a way that we never have to make use of the notion of a constraint force or anything like that. So in order to do so, we defined a generalized force associated to one of the variables qi. So if there are n dynamical variables, then there are n generalized forces, which I called fi. And those are just defined to be the sum on alpha f alpha dotted into dr alpha by dqi. So here, I is an index that runs from 1 up to n. Alpha is an index that runs from 1 up to m, and we are summing over alpha. And f alpha here is the force on the alpha component of the system, which by Newton's laws is m times the acceleration of that component, which is the second derivative of R alpha with respect to time. And near the end of class, as the first step in our reformulation of Newton's laws, we decided that we wanted to try and generalize Newton's law F equals ma to the generalized forces Fi. And the way that we did that is is there a question? Okay.
By the R alphas, do you mean like R1 would be X, R2 would be Y?
Precisely. So I write a vector symbol over R alpha to denote the fact that for each value of alpha, R is a vector. So for example, R1 vector is X1, Y1, Z1, the three Cartesian coordinates that label the position of the first part of the system. So for example, if I have a system where I have two objects that are connected by a rigid rod, then R1 would be the three-dimensional position of one part, R2 would be the three-dimensional position of the other part. Any other questions? So last time we concluded the following. So if we write the kinetic energy as a function of the QIs rather than as a function of the R alphas, then we have something rather remarkable. So the kinetic energy, which, let me remind you, is the sum of 1/2 mv squared over all of the different parts of the system. So it's the sum over alpha of 1/2 m alpha, where m alpha is the mass of the alpha part of the system, times the velocity of that part, which is R alpha dot vector squared. So if we think about that as a function of qi dot, as well as time, because again, the R alphas may depend on the QIs as well as time, we concluded that the generalized force was equal to the following. It was equal to the total time derivative of the partial derivative of the kinetic energy with respect to qi dot minus the derivative of t, the kinetic energy with respect to qi. I went through that derivation a little quickly at the end of class last time. Would you like me to remind you of the derivation? Or you all understood it reasonably well? Okay. So just to summarize, this is the generalization of f equals ma to a generic degree of freedom, which is no longer, for example, just the position of some part of the system in Cartesian coordinates, but is rather some more general degree of freedom. It could be an angle. It could be the distance between 2 points in some funny polar coordinate system. It could be some elliptic coordinate. It could be anything. And the great thing is that as long as we can write the kinetic energy as a function of these generic degrees of freedom, then we have a very simple recipe for computing Newton's law, or the version of Newton's law for this generic degree of freedom. We just take the derivative of t with respect to q dot, compute its time derivative, and subtract off the derivative of t with respect to q. And in a few minutes, I will go through this quite explicitly and show you how this works for several systems of interest. But before I do so, what I would like to do is show you that, in fact, there, in many cases, can be a vast simplification and a much more powerful and useful formulation of this equation. But before I do so, are there any questions? I think that's mine. No questions? Okay. So let's consider the following simplification. So consider the case where the forces that we are considering are conservative. So you probably encountered conservative forces in your more elementary mechanics classes. Let me remind you what a conservative force is. So a force is conservative if the integral of f around some closed loop in the configuration space dotted with dr alpha is 0. So a little more explicitly what that means is that the work done to change the state of the system is independent of the path that we use to change the state. The path through the space of R alphas, so that's a 3m dimensional space that we use to deform the system, or to change the system from one state to another. A little more explicitly, if we imagine the very simple case where we have a particle moving in 2 dimensions, and it starts at some position here, and it ends at some position here, then the amount of work done in order to change the particle from one position to another, in general, will depend on the path that you choose to move that particle along. However, if the force is conservative, then the work done will be independent of the path chosen. So I could either choose this first path or this second path. And the statement that the integral of the force, the line integral of the force, integrated along that path is 0 for any closed closed path means that the work done is independent of the choice of path. Is that familiar to all of you? Yes. So you probably have seen this in your elementary mechanics classes. Okay. So you probably have also seen in your elementary mechanics classes that for a conservative force, the force vector F has a special form. In particular, it is the gradient of a potential. So you are hopefully familiar with the statement in multivariable calculus that if you have a vector such that the integral of the vector around any closed loop vanishes, then that vector is a gradient of a function. So in mechanics, what that means is that if you have a force which is conservative, then F alpha can be written as the gradient of some potential, which will depend on the R alphas. And here, F alpha is the gradient with respect to R alpha. Or if you wanted to write it a little more formally, it would be d by dr alpha of v r1 up to R alpha. Just to be completely clear about what I mean, for example, that the force on the first object has three components, which are the three components in our Cartesian coordinate system, which I could call I, or let's call them K, where K is 1, 2, or 3. And then this is just the derivative with respect to R alpha K of V, which is a function of the R alphas. So this is just another way of writing the statement that the force is a gradient. So are you all familiar from your multivariable calculus class with the statement that a vector whose integral around a closed path is 0 is necessarily a gradient? The converse is sort of obvious. So if you have a force which is the gradient of a potential, then the way that you compute the work done to move a particle from one point to another is by using Stokes' theorem, and it is just the difference. So let me write this down for you. The work done to change the state of the system say from R alpha to R alpha prime is just given by the difference of the potential. So it's V of R alpha prime minus V of R alpha. So of course, everyone's favorite, and this you can see simply by the way I've written it, is independent of the choice of path, because in writing that formula, I make no reference to which path through space I use to deform the system. So all of this is a little bit formal, but of course, in your minds, you all understand it quite well. If I have this thermos right here, and I move it 1 foot in the air, then I'm increasing its potential energy due to the force of gravity, and the amount of increase in the potential energy doesn't depend on whether I take some strange meandering course or whether I move it in a straight line. And that's the statement that the gravitational force is conservative. So, in this class, we will mostly, although not entirely, consider conservative forces. Non-conservative forces include things like friction forces, which, as you may remember, are dissipative and cannot be written as the gradient of the potential. Are there any questions? Yes.
Yes. The equation above there, you wrote f of 1, and then you write
Yes.
the derivative of alpha should be alpha of this one.
So, for example, this is just an example here. Oh, yeah. This is supposed to be 1. I'm sorry about that. Yeah. You can never trust what your professors tell you. You should always be constantly attacking them. Yes, please let me know. Don't be shy about letting me know if I make mistakes, because I will make mistakes. Once in a great long while. Any other questions? Good. So, since the R alphas are functions of the QIs and possibly time, that means that we can write the potential, which is a function of the R alphas, as a function of the QIs and possibly time. So how does this potential depend on the QIs? Well, let's imagine calculating the derivative of the potential with respect to QI. Then, by the chain rule, in order to compute this, we just need to compute the derivative of the potential with respect to R alpha, dotted into the derivative of R alpha with respect to QI, and sum over alpha. That's just the chain rule. So the derivative of V with respect to R alpha is simply the force, F alpha. Crap. I made a little mistake here. The force is actually minus the gradient of the potential. Someone should have corrected me here. I'm sure you guys all knew this. I always forget this fact. This is just part of the definition of a potential. Some silly person defined it with a minus sign 400 and something years ago. So the force is actually the gradient minus the gradient of the potential. Most of you must have known that and just were mean to me and decided not to correct me. Of course, it's just a convention. But we try and hold with convention here in this class, unfortunately. So the derivative of V with respect to QI is the sum on alpha of F alpha, so it's minus the sum on alpha of F alpha dotted into dR alpha by dQi. Is that quantity familiar to anyone here in this class? This is exactly what I call the generalized force. So this is good news. The normal force minus the generalized force. Thank you. You're learning. Okay. This is good news. The normal force, F equals ma, as appearing in Newton's laws, is the derivative of the potential with respect to R. And the generalized force is the derivative of the potential with respect to Q. So that means that for a conservative force, we can then rewrite our equation. So remember that the total time derivative of dt by dq dot minus dt by dq was equal to the generalized force, which is then minus the derivative of the potential with respect to Q. Now, let me make one further simplification. So let me note that since the potential is a function of the Q's but not the Q dots, the derivative of V with respect to Qi dot is 0. So I can rewrite this formula as follows. So the first thing that I will do is I will define a quantity called the Lagrangian, which is denoted L, which is the difference of the kinetic and the potential energy. This L is thought of as a function of the generalized coordinates, their time derivatives, as well as time. And then the equation of motion, which I've written up here, takes a very simple form. It's the time derivative of now dl by dq dot. So that, of course, is just the same as the time derivative of t with respect to q dot, because v is independent of q dot. And then the second term is just minus dl by dq. And all of that is equal to 0. So what does that mean? That means that for a general dynamical system, yeah, if you can figure out how to close that, that would be great. For a generic dynamical system, if we can compute the Lagrangian, which is the difference of the kinetic and the potential energies, as a function of the QIs, then writing down the equations of motion is quite simple. It's just given by this simple formula, which has a name. It's called the Euler-Lagrange formula, or the Euler-Lagrange equation. d by dt, dl by dqi dot, minus dl by dqi is equal to 0. So at first sight, this might seem like a rather complicated formula, but trust me, you will become sick of it by the end of the semester. This formula is a very important reformulation of the basic laws of mechanics in a way which allows us to completely do away with constraint forces, with Newton's laws, F equals ma, and all of that stuff. So let me just make a couple comments. So the first thing that I would like to note is that if we have n degrees of freedom, so I runs from 1 up to n, then this is a set of n differential equations. One per degree of freedom. So if we have 1 degree of freedom, this gives us 1 equation of motion. 2, it gives us 2 equations of motion, and so on and so forth. The second thing that I would like to note is that typically these are second order differential equations for the QIs. So why is that? Well, remember the Lagrangian involves the kinetic energy, which involves the first derivative of Q with respect to time. And so taking d by dt of it will give us the second derivative of Q with respect to time. Although there are more complicated situations one can consider where the equations of motion are not second order differential equations in time, by and large in this class we will focus on situations where the equations of motion are second order in derivatives of time. So this is a very important conclusion. So perhaps what I can do is just give a summary of what we have concluded so far. So this would be a summary of the Lagrangian recipe for writing down equations of motion in classical mechanics. So given a system with some parts, R alpha, where alpha runs from 1 up to the number of parts in the system, the first thing you do is you identify some dynamical variables Qi, which uniquely specify the state of the system, and you write the positions of the various parts of the system as functions of the Qi. The next thing you do is you compute the kinetic energy, which is the sum on alpha, 1/2 m alpha times the velocity of the alpha part squared, as a function of the Qi's. You then compute the potential, which was initially a function of the R alphas as a function of the Qi's. And finally, you write down the Lagrangian, which is a difference of the kinetic and potential energies as a function of the Qi's. And the writing of the equations of motion of the system is then a very simple algorithm given this Lagrangian. It's just given by the Euler-Lagrange equations, of which there is one per each degree of freedom Qi. And although conceptually the Euler-Lagrange equations include precisely the same equations that were in Newton's laws, this new formulation in terms of Lagrangian is both practically an extremely efficient way of determining the equations of motion. It also gives us considerable conceptual understanding of the behavior of mechanical systems. So what I would like to do now is just give you a few examples of this Lagrangian recipe at work. You will very quickly see that Lagrangians are worth learning because they make your life so much easier. Problems which were easy in Newtonian mechanics are trivial in Lagrangian mechanics. Problems which are hard in Newtonian mechanics are easy in Lagrangian mechanics. And problems which are completely impossible in Newtonian mechanics are somewhat less so in Lagrangian mechanics. And after going through a few examples of this Lagrangian recipe, what I would like to do is then go on to discuss some of the more formal aspects. I will show you how not only is this Lagrangian technique practically useful, it is also conceptually useful because it provides us a completely new way of thinking about the mechanics of systems. Before I discuss some examples, are there any questions? This will appear rather formal right now, but within 5 or 10 minutes, you will have a very explicit understanding of how this works. Okay, let's go through a few examples. So let's consider a pendulum. So I'll take a pendulum which moves just on a plane. It has a fixed origin, and it has a weight which is attached to that fixed origin by a rod of length L. And so this is the system. The position R alpha, there's just one position. It is now a 2-vector, which is the position of this weight at the end of the pendulum. And we now have to choose a dynamical variable. So we could choose as our dynamical variable x, we could choose it to be y, but as you will probably guess, the equations of motion will be simplest if we choose our dynamical variable to be the angle theta, which this pendulum makes with vertical. So we now, step one, have to write the position of the pendulum as a function of theta. So that's easy enough. X is L times sine theta. Y will be minus L times cosine theta. And we then have to write the Lagrangian in terms of this variable theta. So first, let's compute the kinetic energy. So the kinetic energy is 1/2 m x dot squared plus y dot squared. We would like to write this in terms of theta. So if you look at the equation for x, you can see that using the dependence of x on theta and thinking of theta as a function of t, x dot will be just using the chain rule, L cosine theta, theta dot. And likewise, y dot will be L sine theta, theta dot, since the derivative of sine is cosine and the derivative of cosine is minus sine. So the kinetic energy will be 1/2 m L squared times cosine squared theta, theta dot squared, plus sine squared theta, theta dot squared. And using the fact that sine squared plus cosine squared is equal to 1, this is just 1/2 m L squared, theta dot squared. The potential energy is even easier to compute. It is just minus it's just mgy, right? This is the potential energy due to gravity, which is just mg times the vertical position, which is minus mgl cosine theta. The Lagrangian is the difference of these two guys. Thought of as a function of theta and theta dot. So the Euler-Lagrange equation is just given by finding the time derivative of the derivative of L with respect to theta dot and subtracting the derivative of L with respect to theta and setting that equal to 0. So the first term is the time derivative of the kinetic energy with respect to theta dot, which is just m L squared times theta double dot, right? Because the derivative of theta dot squared with respect to theta dot is 2 times theta dot, and then the time derivative of that is theta double dot. And then we subtract the time derivative of mgl cosine theta. Sorry, we subtract the derivative of mgl cosine theta with respect to theta. So that's plus mgl sine theta. And if you look at that equation, and you remember deep into the dark ancient ages of history when you took your freshman mechanics class, you will recognize this as simply the equation for a pendulum, the equation of motion for a pendulum. And it has now been derived without any of that silly mucking around with constraint forces or anything like that. Any questions on that? So this was a rather trivial example. Let's now go ahead and consider a more complicated example. So let's imagine that we have a sliding block, so we have something sliding down an inclined plane. That's too easy, so maybe what I'll do is I'll let the inclined plane move. So we have some inclined plane, which is sitting on a table, and we have a little box that's sitting on the inclined plane and can slide down. So I'll call this angle here theta, which is the angle of the plane. And now what we need to do is choose what dynamical variables we would like to use to describe the system. So this system has 2 degrees of freedom. 1 degree of freedom can be thought of as the position that this box makes relative to the length that this box has slid down the inclined plane. Let's call that d1. And if this inclined plane is allowed to slide horizontally, then there's another degree of freedom, which will be the position d2 of this inclined plane with respect to some origin. And I'll let m1 be the mass of this little box, and m2 be the mass of the inclined plane. Okay, so first let's compute the kinetic energy of the system. So it's the sum of 2 parts. The sum of the kinetic energy of the little box T1 and the kinetic energy of the inclined plane T2. T1 is 1/2 m1 times x1 dot squared plus y1 dot squared. And if you just do a little geometry, you can figure out what x1 and y1 are in terms of the variables d1 and d2. X1 is just given by, so first of all, that's the horizontal position of that little box. So it's given by d2 plus d1 times, is that cosine theta or sine theta? Any guesses? I have it written down, but I'm not going to look at my notes because it's more fun that way. Well, when theta is equal to 0, it's got to be 0, so that's sine theta. Right? Okay. Do a little geometry and it'll become pretty clear to you. And y1 will be minus d1 cosine theta. And so that, using the same set of manipulations, so that'll be 1/2 m1 times x1 dot squared, which is d2 dot plus d1 dot sine theta, minus squared, minus d1 dot squared cosine squared theta. Or expanding out the squares and using the fact that sine squared plus cosine squared is equal to 1, it's a plus there, not a minus. Sorry about that. Using the fact that cosine squared plus sine squared is equal to 1, this is d1 dot squared plus d2 dot squared plus d1 dot d2 dot sine theta. And the total kinetic energy, we have to add T2, which is the kinetic energy of the sliding inclined plane. What is that? That's just 1/2 m2 times the position of the inclined plane. So that inclined plane only slides horizontally, so we just need to compute the horizontal velocity, which is d2 dot squared. And the total kinetic energy is the sum of those two things. And to compute the Lagrangian, yes. I missed a 2. There's a 2 there. Sorry about that. Is that what you're going to ask? Okay, good. Thank you. So to compute the potential energy, the inclined plane is not moving in the vertical direction, so we just need to compute the potential energy of the block, which is mg(y1), which is minus mg(d1) cosine theta. So the Lagrangian is just given by the difference of these guys, So let me actually write that a little more simply. Let's write this as m1 plus m2 d2 dot squared plus 1/2 m1 d1 dot squared plus m1 d1 dot d2 dot sine theta plus mg d1 cosine theta. There will now be two equations of motion, from one found by computing the Euler-Lagrange equation for d1, and the other by computing the Euler-Lagrange equation for d2. So the first one, which is the d1 equation of motion, we take the time derivative of the derivative of this guy with respect to d1 dot. So that's m1 plus m2 d2 dot plus m d1 dot sine theta. And we subtract off the derivative with respect to d1. So that would be minus mg cosine theta equal to 0. Or a little more simply, sorry, that m is an m1 there. m1 plus m2 d2 double dot. Oh, I'm sorry. Someone should have corrected. I'm computing the d1 equation of motion, not the d2 equation of motion. You guys are falling down on your job here. Sorry. So that's the derivative of the Lagrangian with respect to d1 dot, which is m1 d1 dot. And so everything there is proportional to m1, so we can just factor it out. And the equation of motion is d1 d1 double dot. Jesus Christ. Okay.